Hello. Shreelakshmi madam, can you hear me?
Yes.
Yeah. Good afternoon, madam. I am Aqleem Siddiqui, the coordinator of this event.
Good afternoon.
Yeah. How are you, madam?
I'm fine.
Yeah. If you permit me, I'll start with the formal introduction in the session.
Sure, sir.
Yeah. Yeah. Good afternoon, everyone. Now we are into the third session of the day. We have with us the guest speaker for this session, Dr. Shreelakshmi. I will give a very brief introduction of hers. Madam has done BTech from Government College of Engineering, Thrissur, Kerala. She did her MTech and PhD from IIT Bombay in Mumbai. Her doctoral research title was Energy Efficiency, Power Quality and Reliability Improvement of Induction Motor Drive-Based Passenger Elevator Systems under Professor Vivek Agarwal from IIT Bombay. Now, as far as her experience is concerned, presently she's assistant professor in NIT Calicut since 2020. She held the position of DST in Inspire faculty at NIT Calicut. Has to her credit journal publications in reputed journals, 3 journal publications, and around more than 6 conference publications. Her area of interest is power electronics application in electric drives, speed control of induction motor drive, trajectory optimization in electric drive, high voltage gain bidirectional DC-DC converter topologies for storage interface, sinusoidal current tracking and controller design, control of special machines like BLDC motor or PMSM motor. She had received Inspire Faculty Award in 2019. As far as professional activities are concerned, she is a member of IEEE and is a reviewer for the journals of IEEE Transaction on Power Electronics, IEEE Transaction on Industrial Electronics, IEEE Transaction on Smart Grid, and IEEE Transactions on Industrial Applications. So this was about our respected speaker at present. I would request her to take over and continue with her session. Welcome, ma'am.
Thank you, sir, for the nice introduction. I hope I'm audible to all of you.
Yeah, you are clear. Yes.
And the screen is also visible.
Yes, madam. Yes,
okay.
It is full screen now.
Okay, fine. So we will be having a session of about 1.5 hours where we will try to discuss the electric drives used in electric vehicle and its importance and how do we select these electric drives for various vehicle applications. Okay, and we at the end, just to understand a kind of a drive system, I'll give you an example of one of the drive systems I have worked with and how I have optimized the operations of that drive system to make it more energy efficient. If there are any doubts, I hope you can, I think there is an option to raise the hand. Then if it is very urgent to be cleared then and there, you can raise the hand and I'll try to clear it then and there. Or I think you can ask in the chat box, which we can answer at the end of the session. I hope that most of you are from electrical background and do understand certain electrical terms. Everybody can relate to. So let us just start by examining a brief history of electric vehicles. I hope you all will be hearing about these things for the past 2-3 days at least, or for the past 1 or 2 years. We have been hearing a lot about electric vehicles in our country. Even all others are moving towards electric vehicle. So just for an introductory part, I'll just say that electric vehicles are not a new technology. They were the one which was developed as a vehicle in 1800, say, or in the beginning itself. We all know DC machine has its own issues, and there were a lot of issues related to storage and other parts because the technology has not advanced at that time. But still, the vehicle developed was electric in 1800, and that we call the beginning stage of the electric vehicle. But by 19th century, by 1901, what happened is that the electric vehicle technology was improving, it was advancing, but still we had not reached the power electronics part of it. So the power electronics or the semiconductor devices were still not found by this time. And the only motor which we had tried to use in electric vehicles were DC motor for the easiness of control. And the storage technology was also DC in nature. Therefore, people could not think about using any other kind of a motor in electric vehicle, and therefore it became slightly stagnant. And at the same time, the petroleum industries had taken the power, and petrol-powered IC engines took up, and therefore the electric vehicle technology slightly became on the secondary side, and the primary importance was then given to the IC engine. But later on, as we were starting to talk about the oil prices and also about the pollution, etc., we again started to think about bringing back the electric vehicle with a stronger technology, because by that time we have all the semiconductor devices available, and the SMD technologies were there. We can make it very compact, and with these new technologies, with these new advancements and new types of motors available, we can make the electric vehicle system as such more compact and efficient. So with this extra amount of technology and extra amount of confidence we have gained by the improvements in the technology, now we are trying to bring back the electric vehicle into the industry, and it's also important from the pollution point of view as well as from the fossil fuel point of view. So everywhere now we try to include the electric vehicle. Okay, so we'll see as we advance in this session, we'll see what are the main challenges which we have when we try to do this now, and what are the possible ways in which we can overcome these challenges. Okay, so another reason other than the pollution as well as the fossil fuel getting extincted, all these are the primary reasons. More than that, when we see the efficiency part of an electric vehicle, that gives us a lot of excitement to shift the complete transportation sector to electric. Now let us just take IC engine based vehicle, which is running through some fuel tank, let it be any fuel, and which is running in an urban driving condition, in an urban driving or in a city driving condition where there will be more number of brakings happening, there will be traffic and there will be signals, so there will be a lot of standby period, etc. So let us consider such a vehicle, a normal IC engine based four-wheeler, which is running in an urban driving condition. Okay, then if the fuel tank, if we use say 100% energy is there in the fuel tank, then it directly goes to the IC engine, because the IC engines are not having a very good efficiency. We lose around 76% of energy in the IC engine itself. So the efficiency of IC engine comes around 34%. And when we have it in the standby mode, again, we lose some amount of energy. So the only 16% of the energy of the fuel, this 76% loss comes along with the other parts of also. like when we burn the fuel, there'll be some losses associated with this. So in total, we get only 16% of the energy, which we can actually extract from the fuel. Okay, so that efficiency from the engine side itself has become very poor. And then there can be some driveline losses, due to the powertrain or the driveline which is there connecting the engine to the wheels. And that if we take it as 3%, even then only 13% of the energy reaches the wheels, in which, because it's an urban driving, 6% will be wasted while we brake the vehicle, and only 4% is there for rolling and 3% for the aero. So that means we use very less amount of, or there is a lot of losses associated with the energy in the fuel tank. We lose only 13% of the energy in the fuel tank. So this is a very rough number. It's not a very exact number, but more or less, if you do the examine the efficiency of a IC engine based vehicle in urban driving, it will come around this. Okay. Now, similarly, same vehicle, if we do it for a highway driving, the only difference is that we can avoid the standby losses and the braking losses slightly, but still we can see that the efficiency is only 19%. Okay, so that bothers us a lot. Having a 19% efficiency for a system is slightly on a very bad, a very lower side. And also we have used this fuel, which is coming from the fossils, which gets accumulated by years. It takes time to come back. So there are a lot of issues also associated with that. So overall, this performance is not that good, but it was economical and it was the feasible one until the electric vehicle technologies are developed. Okay, so before 1950s or so, or before I could say the power electronics or the semiconductor devices became available, all these were affordable. This was okay to us. At least we are getting 19%. That is how we would have thought about it. But now, since we have an option to shift to a better technology, to more green one, we do prefer that. Okay. So the difference between a combustion engine and a battery-powered electric vehicle. So we are now here discussing only a battery electric vehicle. I'm not going to the hybrid electric vehicle here. It's a completely fully electric vehicle which I'm talking about. So here, instead of the fuel tank in an electric vehicle, we'll have a battery or an energy storage system. And the energy in that will be conditioned by some electronic interface, and it will be fed to the motor. And this motor will be driving the wheels of the electric vehicle, and thus the energy gets transferred. Okay. Now, if we see the efficiency of the system, the electric motors have very good efficiency. Okay. Therefore, suppose we take the electric motor to be some 90% efficient, and we don't need to have any standby losses here. It gets turned on instantly. Therefore, we can avoid the standby losses, or even if we consider that, it won't be a big value here. So we get almost 76% of the energy or the efficiency of the system becomes around 76%. Out of it, maybe something like 11% or 15% may go while we do a braking of the system. Now, because it's an electric vehicle technology, we can do some methods like regenerative braking, where we can at least try to bring back a part of this braking energy back, or we can just store it back to the battery. Okay, so we are actually not losing this 11% here. We will try to take it back and store it again in the battery using some regenerative method. So again, we have a benefit of slightly more higher efficiency here. So that's why electric vehicle. Okay. Now, on a broader scenario, if we now we have thought about the condition where we have a fuel tank to the wheels, and we found that from the fuel tank to the wheel, the efficiency is only 16% around for the IC engine based system, and 76% for the electric vehicle. Now, if we think from a broader point of view, from the time frame where this fuel has appeared, so for an electric vehicle, the pure fuel is the electrical energy which is stored inside the battery. So that electrical energy will be something which has to be generated. So there'll be a generating station and a transmission system associated with it. So this is not mine to tank. I'm sorry. This is from the generating station to the tank, to the not the tank, but the what can I say? The storage device, the battery. Okay. So we have we can see that there will be a generating station and there will be some transmission systems from where the energy is transmitted and it reaches the charging station where from where we get the vehicle charged. Okay, so in case of an electric system, we have a better efficiency. If you see 82% efficiency can be associated with the generation if it is an alternator or something like that, and around 98% efficiency we can give to the transmission sector. These are maybe on the higher side, but even then we have around 80% efficiency here. Now, if you take the refining and then transmission is through some truck transport or something, and the refining efficiency is again very poor. We get only 33% there. Therefore, this overall efficiency here will only come around 31%. So 31% of the fuel extracted or mined is the one which is reaching the tank, out of which we are using only 16%. So the overall efficiency is really very bad here. In this case, we have 80% of the energy generated, which is used like 76% of which is reaching the wheels of the machine, wheels of the electric vehicle. The numbers are still not, they are good when we compare it to the IC engine, but they can be improved. Okay. So therefore, we will say that electric vehicle is a better energy efficient, and it is an environmental friendly method for transportation. Okay. Now, what are the challenges which we have for the electric vehicle? So, so when we go for the challenges in electric vehicle, we can first think about what are the parts of an electric vehicle. So one, we have the motor in an electric vehicle. Then we have the energy storage. We have to keep the energy stored in the vehicle. Unlike the other transportations, so like we carry the fuel inside the car, we have to keep the electrical energy stored inside the vehicle. So the other way is like the traction system, but that is quite not possible on roads because it is not very regulated kind of traffic which we have. So we need to have some storage inside. So that is another part of it. Then that storage part has to be charged from some charging station. So that is another part which we will be looking at. So how we want it to be is like we go for filling the fuel inside the car, and we get it. We get the petrol or the diesel filled within some 2 or 3 minutes time and give the payment and come back. So that is the easiness we get when we do a refilling of the fuel tank in an IC engine based vehicle. But in case of an electric vehicle, it's a battery. Battery has its own dynamics. We cannot charge it so abruptly like how we fill a tank. So it will take some time. So that is yet another challenge. So there'll be a motor, there'll be a storage unit, charging system associated with the storage unit will be there. Some of them will be on board. Some vehicles may not have it on board. If we just go to a charging station, it will have all the required charging points according to the battery we are having. And then from the battery to the motor, we will have to condition the power. Suppose a battery, usually the power is available in the form of DC, but the motors may not be a DC motor. It will be something like it can be an induction motor or a BLDC or anything. So it will need power in its own form. We have to condition that power or shape that power into the form required by the motor. For that, we need a power electronic interface. Okay, but power electronic interfaces are available nowadays. The challenges associated with that is only in improvement in efficiency and in easiness of control. But the main challenges for EV here now is one is a selection of motor. The EV has to carry the motor, so it has to be light, it has to be power dense, it has to be efficient, okay, and also it needs to have certain characteristics which we will see. Then next is we need to select the storage unit, so that again has to be efficient and it should be something which can be charged fast. And then the sizing of this storage. If the storage itself acts like the weight to the vehicle. So when I was talking to one or two people from the vehicle industry who are moving to the electric vehicle sector now, they said that the storage itself for around 180 or 200 kilometer drive per one full charge is around 300 kilograms of weight. So that is itself one big load to the vehicle, right? So sizing, if we can reduce the size by even 1 or 2 kilograms, that will improve the efficiency of the complete vehicle very drastically, right? So that is another challenge, sizing of it. How much we want to move, how long we want the vehicle to run under one full charge, and the charging time. So this charging time and the sizing of the storage are the two things which we are now really worried about in the case of electric vehicles. And there has been a lot of researches going on because that is the one which is making us slightly or making us slightly confused when we try to shift completely to the electric vehicle. Because unlike other petrol or diesel based vehicles, we cannot charge it abruptly. We cannot, it will take some 1 hour or 2 hour time for it to charge, depending on the kind of storage and the kind of charging system we are using. It cannot be like dropping in and coming out. So that is one thing which needs to be solved. Now, if you try to solve it, we have to, the only way in which we can charge a battery fast is by increasing the current we feed to the battery. So either it will cause a damage to the battery or the life cycle of the battery will be affected. And on the other side, if we are trying to take this energy from the utility grid, that will have, and there is a lot of charging stations coming up, and all the vehicles are going to become electric, and all of us are going to charge with this high rate of current, then that is going to cause a lot of problem to the power grid itself. So there is challenges from both sides when we try to reduce the charging time. So that is one very big problem in electric vehicle industry. But our focus here is a selection of motor. We try to give you an insight about this, and we have why I am saying about the charging time is that we have one project running here where we extensively look at that, reducing the charging time of electric vehicle. Okay, so I'll just give you a glimpse of that presentation. Okay, now when we try to select the motor for the electric vehicle, we want the motor to have a characteristic of what we say or what we call as an ideal traction hyperbola. So what do we mean by that is we want the traction power of the engine of any vehicle or the motor of vehicle to be maximum always. Okay, so what that means, if you try to accelerate it at any speed, that should give us the same amount of power or same amount of push to the vehicle. It should not be different under different conditions. So for the traction power to be maximum always, or for the traction power to be constant always, we will need to have traction force to vehicle speed curve following a hyperbola. It will be an inverse relation because power is force into speed. So if you want it to be in the other way around, it will have to be like an hyperbola, and this hyperbola where we keep the Pmax as constant is called as an ideal traction hyperbola. So if you see here, this is actually starting from that infinity point, and it will extend, but the limits are put on the upper side of the force by the friction limits, beyond which we cannot increase the force of the traction device, and the speed is limited by the road dynamics. Okay, so we'll have a limit over the speed and limit over the torque or the force of the motor, and the other part is following this hyperbola, and this one we call it as a traction hyperbola. Okay, so we want our operating point to lie somewhere on this hyperbola. The benefit is that we will get the maximum traction power output always. Okay, so for just to get the maximum traction power output, we will be doing all these things. Now, when we reach the IC engine technology, they have a very limited range of speed, and the traction curve for an IC engine is something like this. Therefore, only for some very small range of speeds, we can get the maximum power for the IC engine based technologies. Now, for a normal IC engine, I'm saying about a IC engine without a gear. Okay. Now, to make it follow this traction hyperbola, what we do is we will insert a gear in the out in the engine. Okay, so then what it will do is this curve, according to the gear ratio, it will be shifted either to this side or to this side. So as we know, when we insert a gear, if the speed is increasing, the torque will reduce, and if the torque is increasing, the speed will reduce because the power has to be constant. And there are many ways of reaching that. So keeping that in mind, if you just do the gear ratio multiplication, you can see that if you change the gears, we can have various points where the IC engine curve touches our ideal traction hyperbola. Okay, so that is why we have gears. So when we want to start the vehicle, we want it to have a higher torque, and the speed will of course be less. So it will be somewhere near curve where we such a way that operates at this point around. The operating point comes around here. And as the vehicle starts to move, as the speed increases, if you don't change the gear, what will happen? It will continue to be on this line and it will continue like this. So the traction force which we are having or the torque which we have will be reducing as you try to increase the speed in the first gear itself. So then we will shift to the next gear, which is the second gear. And again, we will operate it for some range of speed. And then again, we can shift to the third gear like that. So when we shift the gears, we are trying to touch this traction hyperbola so that we get the maximum traction power. Therefore, in an IC engine based vehicle, gears are inevitable. We need to have gears in an IC engine based vehicle. The gears can be automated or manual, that is different, but there has to be gears there. Otherwise, it will be really difficult for it to give a good amount of acceleration or a good amount of power at all the conditions. Okay, or it will not be very efficient. Therefore, gears are mechanical devices, right? So that will come along that mechanical transmission system, and that has its own losses associated with it, and it makes the system more bulky as well. So that is one issue which we have in IC engine based vehicle. Now let us come to the speed torque characteristic of electric motor, which we desire to have in an electric vehicle. Okay, so what is the ideal characteristics we are aiming at? We aim at getting a characteristic of the motor which is same as the traction height. Okay, so that we can just change the operating conditions of the motor and reach somewhere closer to the maximum power, traction power, and we can operate it in that way. So we want torque. Torque is something which relates to the force. Okay, just the radius is the one which will be constant in between. They are proportional. And so it is same as the force versus speed graph, which we have already seen in the previous slide. Okay, so torque, now this torque part what we want is to follow this kind of a speed curve or the torque speed characteristics of the electric motor should be having a constant region until some speed, and then it should follow a constant power region where it will follow a hyperbola, and then it will reach the maximum speed. Okay, so how do we name a motor is by a factor x, which is defined as a ratio of its maximum speed to the base speed. Okay, so if you change the x value, suppose the ratio of the maximum speed to the base speed is less, that just means that the base speed is more. So we will have the curve shifting to the right side, and if you have lower value of x, the curve will be shifting to the left side. But anyway, this is the kind of speed torque characteristics which we aim at in getting for an electric vehicle. Okay, now what kind of a motor can give us these characteristics is then the ideal motor which we can operate, right? So if you look at the characteristics of a DC motor until the base speed, something like the separately excited DC motor, it is something very similar to this curve, right? So we can, that is a very, very good choice. Starting torque, we can go series motor, DC motor. Again, by proper control, we can make it follow this characteristics, and it will have a high starting torque too. But DC motors, that's why DC motors were preferred if we take the initial electric vehicles. But they have their own issues with respect to the brushes, with respect to the commutator. It's having a lot of problems. So because of those, we started to use other motor whose characteristics on its own may not match this, but through control, through a electronic drive, through a electric drive system or closed loop control, we can change the voltage or the frequency or the sequence in which we give the energy to the machine, such that ultimately it follows a curve of this kind. So that is where our electric drives have a role to play. Okay, fine. So what are the types of motors nowadays being used in electric vehicles? One very popular, which you all might have already seen, is brushless DC motor. So we use, like as I said, we aim at getting the characteristics of a hyperbola and a constant torque until the base speed, and then a hyperbola until the maximum speed. Okay. Now, any motor through a proper electronic drive can be modeled or can be molded to give us the characteristics of what we desire to have. Okay. Therefore, how complicated it is, or how complicated the closed loop control is yet another very big thing. But still, any motor through the electronic interface can somehow be controlled to reach there. Okay. We then selected that control. We'll see. We have different types of motors. One is DC motor, BLDC, which you might have already heard. They are kind of replacing the DC motors. They are actually not a DC motor. We need an inverter to feed it. We'll see that. Then we have permanent magnet synchronous motor. It is just a variant of a BLDC motor with sinusoidal back EMF. And then we have AC induction motors too, based in electric vehicles. Then switched reluctance motor is a very good candidate. They are not very popular because of certain issues which we'll see. And then nowadays people are also talking about using a polyphase induction motor, which has a phase modulation technique. Okay, so that we can somehow completely gearless when we move to the electric vehicle. Okay, so suppose we get a traction hyperbola characteristics as we want through the control itself, we can avoid the gears. Now, if the control is very complex or the speed range we are getting is not that very wide, we may prefer to use a gear along with the electric vehicle itself. Now, if you want to avoid that too, we can opt for a polyphase arrangement. We will see a polyphase arrangement for the induction motor that can again be adapted for the DC or PMSM or SRM motors as well. Okay, fine. So let us see BLDC motor. So BLDC motors are preferably used in two-wheelers and three-wheelers. Okay, they are used in electric scooters mainly and in auto rickshaws too. Okay, when we compare it with the induction motors, they are slightly expensive, but they are very small in weight, they are compact, and they are very efficient. Okay, so that is why. So why it is expensive is its rotor or the rotating part of it, or one part of it will be a magnet. Okay, it's an active thing. So if you want to just mold a magnet, it needs a lot of protections, because it will attract anything, any metal which is around, right? So that is a very big technology which has to be there. So that adds to its cost. And also they are available more nowadays, and because of all these, they are not used in because of the cost as well as the efficiency coming around 85 to 90% only. They're not being used in very heavy vehicles nowadays. They are being used in two-wheelers and three-wheelers mostly. So the examples of the scooters which use a BLDC motor is these are have a BLDC motor in it. Now there are two types of BLDC motors which we will be using in scooters especially. One is hub type, which is like the ceiling fan, where the rotating part and stationary part is inside. So the wheel can be directly put on the rotating part of the motor, and it is used in this 22 motors. They use hub type of motor. Or there are BLDC motors which is having an inner runner type, where the rotating part is inside and we bring the rotation out through a shaft, and then through some connect it to the wheels and make it rotate. Okay. Now, so why BLDC motor is because of control. So if you see here, this was actually an animation. I don't know why it is not running now, but I'll just tell you using a pen here. So we have, suppose we are having a magnet here. Okay. And like this. And this is having its north pole to this side and south pole to this side. Okay. Now, because this is south, it will be locked. And because this is north, it will be locked, right? Now, in the BLDC control, the only thing we do is to shift the south pole to the nearby coil so that this attraction is locked, and this coil will attract this north pole, and then it will move one rotation. Right. Then again, we shift the south pole here. So that is the way we do. So we have to sense the position of the rotor and then give the sequence of firing to these coils accordingly. And that will help in giving the rotation. So so we don't need a very complicated control scheme. What we need is only some information about the rotor position, which we get from the Hall effect sensors. There are 3 in number, at least. There can be more also, but at least we may need 3 sensors to give some accurate detail of it. And according to the values we get from the Hall effect sensor, we detect the position of the rotor. Then we will energize the poles of the stator in such a way that it rotates in the desired direction, and the speed at which we change this energization will increase or decrease the speed of the motor. So here we don't need a very high complicated control. Control becomes very simple and is called as a trapezoidal control. But we need to change this excitation to this coil. So when I say we want to shift the pole, we will have to reduce this current to 0, increase this current in one direction. Now, if you want to make this as a north pole, we'll have to increase the current in the other direction, right? So we have to change the current direction. You have to change the magnitude of the current. So to do that, we will have to have some kind of a semi-conductor device which will control the current flow. Okay, so what we will do is we will just change the direction of the current. We'll just switch. We'll not change the bother about the magnitude of it. Okay. So we'll just change the direction of the current for a very simple control, and that is workable too. In that case, what we need is just to switch the current between these. To do that, we will need, so now we are having 3 phases here or 6 coils here. So we will need 6 switches that will form like an inverter circuit. Okay, so that switches will be a semiconductor device that comes from the power electronics, and that gives us, helps us in this one easiness we get from the BLDC motor. Now, when we look at the permanent magnet synchronous motor, PMSM, they are a variant of BLDC. The only difference is that the back EMF or the kind of windings which we have in PMSM is continuous winding. It's not a discrete winding like we had in a BLDC. It's not a concentrated winding like this. In the PMSM, we have a continuous winding, like what we do for a 3-phase induction motor stator. We do a 120-degree shifted 3-phase winding of the stator. So because of that, it's not a very discrete shift in current which we will need. We will need to feed a current which is sinusoidal. So what we want is a sinusoidal supply from a DC. So we use an inverter. So we'll have the battery and we call it as a battery. Then we'll have the inverter here. It's a 3-phase inverter, controlled one. And then we use this output of the inverter. We have 3 lines coming out to feed the phases of this PMSM drive. So controlling this inverter switching, we can control the speed of the PMSM driven vehicle. Okay, so this control, we use something similar to what we use in induction motors, but we get slightly higher benefit with respect to the torque ripples here when we go to the PMSM. Okay, so people prefer to use PMSM in heavy vehicles like cars and buses, and that is now being used as well. So PMSM is just a variant of BLDC, and it is being used in 4-wheelers and in buses. Okay. Then we have AC induction motors. So AC induction motor is also a very popular candidate, and it is being used in so many 4-wheelers nowadays. In most of the Tesla models, we have induction motors itself. Even though these machines like BLDC and PMSM are replacing the induction motor in most of the industries, induction motor is still a very good player because of its ruggedness. So when we choose a motor for the electric vehicle, we'll also look in the condition where whether it is okay to operate it at various temperatures, various ambient conditions as well, because the vehicle can travel anywhere, and it can also, the machine or the engine will be somewhere enclosed. So the heat transmission, the temperature control, jerk, whether it will tolerate certain amount of jerks, so all these are a matter of concern. So when we look at all these things, induction motors have a very good record, and that's why still they are not being replaced by these machines like BLDCs or PMSMs in some of the vehicles. Okay, so the control of an induction motor is slightly more complicated than that of a BLDC or PMSM. So that is one thing which keeps it slightly now we have a very good microcontrollers available. We have very good electronic devices available. So because of all these reasons, still induction motors are being used as a reliable solution for the electric vehicle technology. Okay, so we see that there'll be a 3-phase winding in the stator of the induction motor, and when we feed the three-phase supply, it will give a rotating magnetic field which will rotate the rotor. So this supplying the three-phase supply, its voltage value and its frequency will all help in getting desired speed. So there are various techniques through which we can control the voltage and frequency of the supply, and we can reach a characteristics of the induction motor which is somewhere closer to the hyperbola characteristic. Okay, so if we use a V by F control, we can manage to get a characteristic similar to the traction hyperbola characteristic. Okay, fine. Then we have a switched reluctance motor as another candidate. They are being used very rarely. They are used in Tesla Model 3, but the benefit what we get when we shift to a switched reluctance motor is that the rotor is just a laminated steel. It is not having any winding in it. It is not having any permanent magnet or anything. It is just a laminated steel which is there. So because of that, the inertia of that rotor is very less. It's not very lightweight. So that is one very good benefit we have for the switched reluctance motor. But the complexity of control is something which is a big drawback for the switched reluctance motor. Okay, but once we solve the drawbacks of the switched reluctance motor, it has a very good potential in replacing the PMSM and BLDC motors in electric vehicles. Okay, then we have this polyphase motor. So what we do is a pole phase modulation technique for the polyphase motor. So how do we do that is we will change the number of poles as well as the number of phases in a certain ratio, so that I don't know how many of you will be familiar, but mostly in our machines lab, we will do a pole changing experiment for the control of the speed of an induction motor. So when we change the pole number of poles, we will get the benefit of having a higher or a lower speed of the induction motor, right? So we do that by we don't change the complete winding of the machine to change the poles. We just have some parallel parts coming out, and we'll just change the way in which they are connected in series or parallel to change the number of poles. So that they are called as pole amplitude modulation, where we only change the number of poles, but in both the cases, the number of phases are 3 itself. But in pole phase modulation, we change both the number of poles and the number of phases. And what benefit we get is we get 2 types of motors. One with a lower number of pole and higher number of phases. The other one the other way around. Okay. So how do we design this? We will select, so the number of slots in a machine in the stator should remain the same, right? We are using the same machine to get the different pole phase modulated scheme. So when we do that, what we get is we need the number of slots to be same, and number of slot is actually number of phases into pole pairs into slot per phase per pole, right? Q into mx into px is actually s, and that has to remain constant. So for one kind of pole phase modulation and for the other, always the multiplication has to come has to be s, which will give the equation like P2 by P1 is M1 Q1 by M2 Q2. So the design step is like we will choose the K value first, and we will choose the number of slots. Then we can see what is the kind of poles we want to change. So accordingly, we'll choose the K value. And then we will see what is the number of phases we want, what is the ratio we want, and accordingly we will find out what is the slot per phase required. So that is the kind of design we do. How do we change or how do we attain this is just by giving the supply to the windings in two different ways. So we don't get a polyphase motor in a market. Okay, they're not very widely available. So one of the ways in which we can get a polyphase motor is we can get a normal induction motor and then rewind it to get the of a normal induction motor where we have around 36 slots. So we are just showing 18 out of it and 120-degree separation. So if you give the supply to the A phase here, then the B phase supply will be given here and likewise. Okay, and we will have 4 poles. So there are 2 poles here, 2 poles on the other side. Now, if you just draw the winding diagram of this by keeping the sequence and draw the direction of current, you will see that all these will be in one direction and all these will be in the other, and we get a total of 4 poles here. Now, with the same number of slots, we are now using the same stator and rewinding it to get the increased number of phases. Okay, so when we, how we do that is we connect. So when we want to increase the number of phases, so when there are 3 phases, then 360 by 3, 120 is the slot angle, right, between A and B. Now, when we have 9 phases, it is 360 divided by 9, which is 40-degree angle. Therefore, the second winding has to come here. B has to be here, and then C has to be at 80, D has to be at 120, E has to be at 160. So likewise, that winding has changed now. Now, if you use the same motor with the same kind of winding, but you give the supply, now if you want to use it as a 9-phase induction motor, what you will see is that you will have to give supply as 9 phases with 40-degree separation. But if you use the same motor and give supply as 3 phases with 120-degree separation, we will get a 3-phase machine. And if you check the direction of current in this, it will come out to be 12-pole machine. So we have 2 combinations now available. Either it can be a 9-phase 4-pole machine, or it can be a 3-phase 12-pole machine. Okay. 9-phase 4-pole or 3-phase 12-pole. So based on all these things, now if you have these 2 options, the benefit is we will prefer to use the lesser number of poles and more number of phases when we want to operate it at a higher speed and a lower torque. Okay, we will prefer to have lower number of phases and higher number of poles when we want to operate it at low speed and high torque. So basically, we will give supply of this kind for the starting of the machine when we want to start it, and then we'll go shift to this one. So we get 2 kind of hyperbolas then, and then we can just operate it accordingly to get the maximum power. Okay. So that is a benefit. So in polyphase machine, we are completely avoiding the requirement of gears in the polyphase machine. So just a summary of it, we want to use 2-wheelers, we will use BLDC motor. 4-wheelers, we will use both induction motor and PMSM. It's a very heavy vehicle, we will use PMSM. Then SRM motors, if technology advances, can replace a PMSM motor, and to reduce the number of gears and to increase the performance, we can include the polyphase option in all these motors. We can buy the stator of any of these motors, rewind it in the way we have seen to get the polyphase or pole phase modulation and get all the benefit of a pole phase motor. Okay. Now we have discussed the motor of a system. Then the second part of it is a drive. So now we have a motor. Suppose we have an induction motor in hand and I want to use it for a four-wheeler. The induction motor on itself has a torque speed characteristic of this kind. It's not a triangle, but I hope you understand. It's something like this. So if you see, this is torque and this is speed. So it is having a torque speed characteristics of this way. And what we desire is to get a torque speed characteristics of this kind, right? Of traction hyperbola is something like this. So I want to shape this torque speed characteristics to this. That's then only we get the maximum traction power output always. Or induction motors, why they were not very popular, even though they are very rugged when we compare it to the DC motor, is the reason is that the people didn't know to control the speed of the induction motor until there are drives available. Okay, so with the availability of power electronic drives, what we try is to change the torque speed characteristics of any motor. If you take a BLDC motor, it is having a torque speed characteristics like this. So we will all try to, so it will just shift in this way. That's all. We try to change the voltage supplied and the frequency in such a manner to shape this torque speed characteristics of various motors into the one which we require. So that is the role of the power electronic drive in it. Then why power electronics? Why not any other devices? Is because power electronic devices are ideally lossless. So when we try to condition the power from the storage to the load, we don't want that conditioning unit to be lossy. So that is why we have power electronic devices here, and an electric drive system, like what I said, will be having a feedback control, and the aim of that control will be to shape the torque speed characteristics into the one which we want. Okay, so we will suppose we want to control the speed, we will feedback the speed. We want to control this the torque, we will feedback the torque, and there will be some controllers to which we have already given the reference speed, and then that is the desired speed we want to attain. And for that speed, we will want to fit that speed into the maximum power hyperbola, so it will generate the required torque in that way. And for getting that particular speed and the torque values, the power electronic converter will give the supply in the form of voltage, frequency in the required way to the motor. Okay, so this is the overall modern electric drive system for an electric vehicle. If you take any of these, we will all have all these elements in it. And mostly this power electronic converter, which is used in almost all these drives, whether it is a BLDC, PMSM, induction motor, or SRM, or let us take the case of a polyphase modulation also, they're all inverters. The one reason is whether we have the DC input power here mostly. So they and we want the motor will be having a three-phase kind of a winding in most of the motors. So we need three-phase supply here. The way in which the supply is given will be different for different motors, but most of the times the power electronic converter which is available here is a inverter. Okay. So there are various choices for power electronic converters depending on the kind of drive and the kind of source available. And the one which is most popularly used is this one, which has AC to DC to AC conversion, where this DC is can be a variable or a constant supply. So in the case of an electric vehicle, we are having a DC source available, and most of the motors which we use will need power in the form of AC. So a DC to AC conversion, which is an inverter, will be the one which is used. Okay. Then the type of the inverter, control of the inverter, choice of the inverter is all again a very big wide area in which there is a lot of work going on. Use of multi-level inverters, use of certain kind of a control strategy in the inverter, reducing the switching losses. All these are there. All these are very important researches happening, and they are having a very wide scope as well. Okay, so here I'm just giving you the glimpse of an idea about the power electronic converter, which will be used in the electric drive systems in electric vehicle. Okay, now just to give you an understanding of a kind of a drive system, we'll just take an example of an induction motor based drive system, which is an elevator system. So this is the one on which I have worked on in my PhD, and we have a system of we had made a system of this kind where there was an active load, which is an elevator system. So this elevators as well as the electric vehicles have a very close relation, because most of the operating conditions we can relate to. If you check the 4-quadrant operations of an elevator or an electric vehicle, we can just see the analogy. There are so many common points there. Okay, so when we in our system we used an induction motor, and the induction motor was driven by an inverter. Inverter is made up of 6 semiconductor switches here, and then this inverter was fed from the DC supply, which is coming from the main supply, which is rectified. Okay, and there's a certain arrangement for the regeneration part. So when there is a regeneration, because there is a diode bridge rectifier here, it cannot feed the power back to the grid. So it was supposed to be stored in an intermittent storage, and that is the arrangement there. Okay, now this inverter control is the one which controls the speed of the motor, and this is our drive system. Then this is the inverter drive. So if you see, the system is capable of operating in various modes, especially what we are interested in now is in the normal operating mode, where it will just drive the motor at a constant speed. And then when there is braking or when there is a regeneration, so when in the case of an elevator system, the regeneration will happen when there is a heavy car, a heavy elevator car moving down. All right. So if you just imagine a pulley of that kind where one side is heavier, that will naturally flow down. There is no requirement of a motor to make it flow down, right? But it will drop in a very high different acceleration, and it will not be a very comfortable experience for the people sitting inside. So what the motor does there is to brake this. It will give a torque in the reverse direction, so that this natural falling elevator car is that speed is checked by the motor itself. So what it gives is a braking arrangement, and that energy can be used to you make the motor operate as a generator and then feed it back to the storage unit. So same thing happens when a vehicle moves downhill. When there is a slope where the vehicle moves down, again, it is capable of moving down without any motor itself, right? But it won't be a controlled movement. So what we do through our engine is we will try to control the speed of that vehicle. So when we do that, we do a braking action there. So there is a region, so that is capable of doing a regeneration. So a heavy elevator car moving down can be similar to a car moving downhill. Okay, an electric vehicle moving downhill. So most of these operations, motoring and regeneration and all, have almost similarities here. Okay, so what we aimed at is to do the normal operation from the supply, and whenever there is regeneration, to store it back to the alter capacitor. And in the case of an elevator system, we don't want the elevator to be standstill when the power fails. So there was a write-through mode provided. And suppose this write-through was supposed to be provided by the storage unit. Now, if the storage is not sufficiently charged, it may not give the necessaries to write-through operation. So to enable that, we will just connect the UC or charge the UC from the main supply during the normal operation itself under a very under some conditions. Okay, so our aim was if you see this drive system, the reference speed is the input to the controller. Okay, now what is the reference speed we can give? If it is a car on which you are driving, the reference speed is set by there are two modes in which a car can be run. If it is a very long highway, there is a cruise mode where it will operate at a constant speed always, or we give the torque. We don't decide the speed. We will just do the acceleration and deceleration and look at the speed at the speedometer. So now we are talking about the cruise mode, let it be. So we operate at a constant speed. So that speed reference is set by the person sitting on the car. Or in the case of elevator system, it is a predefined speed reference will be there, right? So there will be a predefined way in which we reach that speed reference. So this can also be there for a traction system. Suppose you have a metro train starting from one station and reaching the other station, it can follow a predefined speed trajectory. Similarly, if it is not a city drive, if it is some other kind of a closed driving system, then again, which has stops at a common points and we don't expect much traffic in between, then again we can have a trajectory of the speed in mind. Maximum speed should be this. It should be reached in this much time. So it should be accelerated like this. So if we have that kind of a planning there. So that kind of a trajectory is what we plan. And this trajectory is what we give as an input reference to the drive. Okay. Now, in the case of vehicle also, we can do that. So we can find out the trajectory in various ways. So, and we will give that as an input to the reference to the system where this is an FOC implemented. And this reference was generated keeping in mind the optimization scheme. So same thing is adapted to the vehicle technology too now. When we have a predefined traction, when we have a predefined operating conditions, then we can find out the optimum operating condition for the particular motor and for the particular load torque, so that the motor is operating at its maximum efficiency. So we find out what is the speed at which the efficiency of the device or efficiency of the machine will be maximum. Like if you see most of the vehicles, we see an economy tab in it. In the same way, so we'll just find out that value of the speed and give that and how to reach that speed, the acceleration and deceleration technique too, and then give that as an optimum solution. So that needs some kind of a dynamic optimization that was done for the elevator system, and we give that trajectory as an input to the input. I'll just give you here input to the this whole scheme, and then the control feedback control of this inverter will ensure that the speed of the elevator has reached this reference speed. Okay. And that will be the optimum speed of that elevator system. Okay, so when we try to operate it at that optimum speed, what we observed is that we have got so many the energy loss of the whole system has reduced sufficiently when we try to operate it at those optimum conditions when we compare it with the original one. So we get so much benefit, especially when we try to operate it at the lower loading conditions. So if a four-wheeler is there, if the amount of load is less, then this optimization has a little bit more advantage when compared to the full loaded condition. That was what observed in the case of a elevator system. Okay, and then we tried to find out the kind of current which it takes for the optimum and non-optimum, and it was found that for the optimum condition, the amount of current it takes was less, which clearly indicates that the amount of energy it has is more, then the amount of power loss it has is less. Okay. Now, just an insight to the DST project which we are doing here is on electric vehicles. We are planning to make an electric vehicle which runs inside the campus of NIT Calicut. We are planning to use a BLDC motor based three-wheeler as a beginning, and the aim is to reduce the charging time. Okay, so as I said, charging time is a very big challenge to the electric vehicle. So our actual final aim is to make this electric vehicle charging time so less that it charges while it stops at the station. Okay, so while it stops at one bus stop or one station, and the people gets out, and so there are some people getting in. So let us say that the stoppage time is around 30 seconds. We want the vehicle to be charged in that 30 seconds itself. So that is a challenge which we have taken up. And for that, what we plan is we will find a route map in the campus, place some 5 charging stations in the route map, and we will make the vehicle go along this route map, and at every charging point, it will stop for 30 seconds. And in this 30-second time, it will be full charge, and then it can move to the other stop. So the benefit we get here is that we need to carry this amount of storage for just a movement from one charging station to another only. So the weight of the onboard storage will be reduced by at least 1/15 of the value what it was being used before. Suppose we don't get this benefit of fast charging, we will have to charge it for 1 or 2 hours so that it can run for this complete route map for 2 or 3 times, right? So that means that the amount of battery it has to carry will also be very huge. Now, if you get this benefit of lower charging time of this kind, then we can reduce the amount of storage on board, which will again increase the efficiency and will increase the overall system performance. So the charging point here is planned to be having a PV panel which is renewable based charging point is what is aimed at, and we plan to use ultra capacitors as the storage unit here. Okay, so that is yet another very big challenge to be adapted. So we want to make an ultra capacitor bank. There's a balancing problem. There are a lot of issues associated with this, which is quite interesting, and that is what we are trying to solve. Okay. Because we are saying that the route map is pre-planned and it's inside campus, we don't expect to have an intermittent stops in between. Therefore, we also plan to find out an optimum trajectory, speed trajectory, which the vehicle can follow so that the vehicle will be operating at its maximum efficiency. Okay. And then there is a lot of electronics also associated with it. So with this, I think I can conclude and I can answer your doubts if there are any. So, yeah. Yes, sir.
Participants can ask the question through chat box, or you can raise your hand so that I can unmute you all and you can directly ask the question to madam.
Yes. So I cannot see the chat box here.
I'll read out for you.
Okay, fine.
Hello. Participants, kindly ask your question or raise hand. Yeah, I think there is no question from their side.
Okay. Okay.
So we will end this session over here.
Yes.
I once again request if anybody, yes, attendee number
There is one hand
F050
raised.
wants to ask a question. I'll just unmute. Yeah, you can unmute yourself now. Attendee number 52.
Hello, am I audible?
Yes, yes, yes.
Last example, you have just cited that the vehicle stoppage would be, that is, vehicle will stop for 30 seconds for charging.
Yeah.
I think, is that assumptions or you are going to do like that?
We are going to attempt that because we want it to be charged in that 30 seconds duration.
You are taking it to minimum time or what? What I think is that when a vehicle is stopping, people will be alighting, people will be coming inside that vehicle. So at least one person, if it is going up and down, at least some 5 seconds I have to take, 4 to 5 seconds.
Yeah.
Then you are stopping the vehicle, then you are starting the vehicle. I think that time limit, that charging time limit, what you are in setting, 30 seconds, I feel it is inappropriate.
Yeah, we have actually checked certain standards where if you see a metro kind of a system which is running, and if you see the stoppage time of that, it is coming around 22 seconds. So we have tried to match this with that. So that is why we have kept it as 30 seconds. Another reason is that since it's an inside campus travel, it may not be, and we are only planning for some kind of a three-wheeler arrangement where we will not have so many people on board. So we may not have so many people coming in and alighting and coming up. So we are keeping it very high. I know the limit. So we are trying to attain that. If we can attain 30 seconds, so getting anything lesser than that or more time with the lesser current will be an easy thing for us to do.
Will it be sufficient? What I feel, 30 seconds will be sufficient for that vehicle that has been calculated.
Yes, because we are trying to use ultra capacitors there, and we have done the preliminary calculation, and even we have made one setup where not on board vehicle, but we have charged ultra capacitor bank of the size which we need, and we were able to attain something like 42 seconds by now. So we will try to reduce it and make it 30 seconds. So as I said, the amount of energy we need to carry has also reduced sufficiently because we are charging it at every point. Therefore, the size of that whole system, whole storage system has reduced. So the kind of challenge we get with say a 150 watt hour battery is not there now. We have reduced that amount of energy we need to carry. So that is the one benefit we get here.
Nice. You are again charging by solar panels. That is also a good idea.
Yeah, solar because carbon
So we are
footprint.
going to the world is moving to renewables, no? So that is
Yes,
also a
yes.
good idea, I feel.
Yes.
Nice.
Yeah. Anything else?
Any other question? Any participant would like to ask a question? Okay. So thank you, madam. Thank you very much for coming and taking the lecture during our course.
Thank you, sir.
And sharing your knowledge with us. And it was very nice hearing from you. And we look forward to
I think there is one.
calling you. There is one more, Nilesh sir, just a minute. I'll allow him to unmute. Yeah, Nilesh sir, you can unmute. Nilesh sir, you can unmute now. Press the unmute button.
It is Nilesh Varkute.
Varkute, yeah.
Okay. Can I unmute? No, I cannot.
We actually that we cannot do.
Yeah.
Nilesh sir, you have been allowed to unmute. You can unmute from your side.
Okay, so you can give my contact. Then I think you can.
Sure.
There'll be some connectivity issue or something.
Yeah, he's telling that he's unable to unmute. So maybe some technical issue from his side. Anyway, I'll pass on any queries if I receive after this also, and
yes,
we
sir.
will just post the reply in the group.
Yes, yes.
Okay. Thank you very much, madam. On behalf of Father C. Rodrigues, Department of Mechanical Engineering, thank you for coming and gracing the occasion by your presence and sharing your deep knowledge. Thank you very much. I'll close the session now, madam.
Thank you.
Participants, the feedback form has been posted on WhatsApp chat. So just give your feedback, and tomorrow morning we'll be meeting at 10 o'clock with the first session of Dr. Sheldon Williamson. So the session timings will remain the same, all three. So see you all tomorrow morning. Bye.